In this video, we are going to cover the physical chemistry part of the syllabus. Last time, we covered, as I told you, that the syllabus is made up of 3 sections. The physical chemistry part, which also involve the mole concept and stoichiometry. The second part of it, which is the B part of it, which is inorganic chemistry. And the third part, which is the C part of it, is organic chemistry. We've done with B and C. Today, we will be covering the physical chemistry part of it, involving the mole concept and the stoichiometry. First of all, I would like to apologize for the poor quality of the paper I received. So today, as we'll be doing that, we will go into some miscellaneous related questions. After solving the GCE questions, we will now move to some few miscellaneous related questions. Before we continue, I really want to thank those of you who have subscribed to our channel. We really thank you once more for the love you have for us. Then for those of you who haven't subscribed, please support us by liking our video, sharing to other fellow learners, making comments, and subscribing to our channel. Welcome back. Thank you for taking your time to subscribe. Let's get started. We're starting with question number 1. A 5.00 gram sample of an iron ore was prepared with hydrochloric acid and filtered. The filtered was made up to 250 cm cube in a volumetric flask with distilled water. A 25 cm cube sample of standard solution required 27.30 cm cube of 0.020 mole per dm cube dichromate 6 solution for complete reaction. 1. Calculate the amount in moles of dichromate 6 ion used in the titration. 2. The amount in moles of iron 2 ions present in 25 cm cube of solution. 3. The mass of iron 2 carbonate present in the ore. Yes, after reading the question, after reading the first section of the question, you realize that this has to do with redox titration. Dichromate 6 is there. It's a strong oxidizing agent. Dichromate is a strong oxidizing agent. Now, this is a redox reaction, and I told you that titration, every titration will need a balanced equation. Be it acid-base titration, be it redox titration, you must have a balanced equation. This is titration that has been carried out. The oxidizing agent there is dichromate 6. This one is acidified because it was acidified in the preparation. Dichromate 6 ion. So now they have asked us to calculate, they have asked us to calculate the amount in moles of dichromate 6 ion used in the titration. So now, the first thing we are going to do now is, you know that for dichromate, the concentration of dichromate has been given as 0.020 mole per dm cube. Dichromate 6. That is the concentration. Again, the volume of the dichromate has also been given. They said 25.0 cm cube sample of the standard solution required 27.30 cm cube of 0.020 mole per dm cube dichromate. We have been given the volume of the dichromate that was used up in the titration that reacted with the titrant, with the analyte. Now we have the concentration of it. Remember, I gave you let's start here. There is a formula that says concentration is equals to moles, the number of moles divided by the volume. The number of moles divided by volume. And the volume should be what? In dm cube. It should be in dm cube. Volume in dm cube. That is, you have to convert the volume. If you want this expression to work, you have to convert the volume to dm cube. And 1 dm cube is equivalent to 1000 cm cube. So you have to divide the volume by 1000. Okay. Now, we have been told, calculate the amount in moles of dichromate 6 ion used in the titration. Very good. Now, we have to rearrange this equation. To give us the number of moles. It implies that the number of moles, this implies that moles will be equal to concentration times the volume in dm cube. The volume in dm cube. So in that case, concentration equals to, moles equals to concentration times volume in dm cube. Now we have been told that the volume of the dichromate 6 is 27. So in order to do this, and the moles is 0.02. So what do we do here? What we are going to do here, the number of moles will be the number of moles will be the concentration, which is 0.02 times the volume. You divide the volume is 27.30. So we have to divide the volume by 1000. That will be 27. Let me do so that you cancel out everything which is there. Okay, back again. Okay, now I say the volume is, the concentration is 0.02 moles per dm cube times the volume is 27.30 cm cube. Since we have to convert it into DMQ, we need to divide it by 1,000. In that case, we are dividing it by 1,000. And that will be what? So by 1,000. So now 1,000 cm cube, 1,000 cm cube. So now all these will also cancel this out. So now we will have, if we do that very well, we will be having 0.02 times 27 divided by 27.30 divided by 1,000. We will have 0.0273, which will be equals to that times 0.02. Our number of moles will be, the number of moles here will be 5.46, will be 5.46 times 10 to the minus 4 moles. 5.46 times 10 to the minus 4, or you can say 0.00055 moles. Yeah, you can have that. So you can have that. Now we have that those number of moles. That is the moles of those are the moles of dichromate. The number of moles of dichromate. Okay, now that is the number of moles of dichromate. Now we now go to the second part of it. The second part of it says the amount in moles of iron 2 ion present in 25 cm cube of solution. Now, here, this is where the equation will now come. This is where we are supposed to write an equation. The number of moles, we don't know the number of moles of dichromate that reacted with iron. So in that case, dichromate, the first thing is we need to write a redox equation to know the number of moles that were reacting. In this case, we will have to say, now, dichromate is that is a reduction. Okay, reduction. For reduction, the dichromate is going to do what? It's going to be reduced. We have dichromate is going to be reduced to what? It's going to be reduced to what? To chromium 3. This is chromium 6. It's being reduced to chromium 3 plus. So now, why do I say it is chromium 6? It is chromium 6 because chromium here, we have been indicated that is chromium 6. That is 2x minus 14 here equals to minus 2. 2x equals to what? This is 12. X is equals to plus 6. So that is why we say it is plus 6. So now, what we are going to do now is, let's balance this for redox. Let's balance this equation for redox. Now we need to balance oxygen with a molecule of water plus water. That is the rule. We need to add water there. It is acidified. Now, oxygen is here. Oxygen here can only be balanced. We need to balance with water. Now, there are 7 oxygen here. There are 7 oxygen here. There's only 1 here. We need to put a 7 here. We need a 7 there. We put a 7 here. Now, we need to balance then chromium. There are 2 chromium here. We need to put a 2 here to balance the chromium. Okay. Now, we need to balance, with hydrogen on the left. There's no hydrogen on the left, so we need to balance hydrogen on the left. So now we put hydrogen, and according to the rule, in acidified medium, we balance hydrogen with a proton. Proton is hydrogen ion. So we balance hydrogen with a proton. So we need to add a proton there. Plus a proton here. That is, there's a proton there. There's a proton there. Now there are 7 hydrogen, there are 2 times this, altogether 14. So in that case, we need to add 14 protons here. There are 14 protons here. There are 14 protons there. Now, everything now is okay with this. It is okay with this. Let's go now to what? To oxidation. Oxidation process. Oxidation. For oxidation, it is ion that is there. Ion. So for oxidation process, we need to take ion 2. So ion 2 plus does what? Is oxidized to ion 3. Is oxidized to ion 3. Okay, now there's nothing we can do. Ion 1, there's 1 ion here, there's 1 ion on the right. Ion is okay. The last stage is that after balancing all the ions, the next thing we do, the atoms, the ions, everything, the next thing we do is to balance the charges. Okay, let's see the charges here. On the left hand side, on the chromate, the charges here are, we have 14 plus, then we have 2 minuses. So 14 plus 2 minus, we have the difference is 12. On the right, we have here, there's only 3 plus here. 3 plus times 2, we have a plus 6. No, 3 plus, we have a plus 6. So now we have a plus 12 on the left and a plus 6. You know, we can only balance the charges with electrons. So electrons are negatively charged. So what do? We cannot add electrons here, because we add electron here, because they are negatively charged, they are going to bring down this charge here. So we need to add here so that to make the charge here be equal to the one on the right. What do we do here? We need to add electrons there. And then what electron do we add? Electrons are negatively charged. We have a plus 6 here, and we have a plus 12 here. So we need to add an electron there. So how many electrons? We have 6 electrons there. Let's add 6 electrons. These 6 electrons are negative charges. This negative charge, 6 plus 12, will give us plus 6. And here is what? Is 6. Charges balanced up here. Now here, what do we do here? The charge here is just what? The charge is plus 2 here, the charge is plus 3. So in order to balance this plus 2 and plus 3, let's reduce this one by an electron. We add here. So now everything is okay. But how can we cancel out these electrons? We need to cancel out the electrons. And how can we do that? We need to multiply these by factors that will cancel out the electrons. For instance, here we have 6 electrons here. So we need to multiply the first one by, a factor of 1 times a 1. It remains. Then we need to multiply the second one by a factor of 6. I say times a 6. So now it will remain, and if we multiply it by 6, it will be 6 Fe 2 plus to give 6 Fe 3 plus what? 6 electrons. Now, this electron can now cancel out with each other. The electrons here, the electrons up here will cancel this one here. So these are the two equations we are working with. This equation and this equation. So now let's write our equation for this two. Our equation for this two will be, our final equation for this two will be chromium, that is chromium dichromium here, O7 2 minus plus, how many ions are here? We had let's like the chromium, this and this one, plus 6 Fe 2 plus, here now we'll now go to the plus a hydrogen ion, which is 14H plus, up here this one has been cancelled. We go on the right to give 2 chromium 3 plus ion here is what? 6 ion 3 plus, then the last one here is what? Plus 7 water. So this is our this is the equation we are supposed to use. Fellow learners, make sure you know how to write your to balance your equation using the half equation method in balancing redox equation. Half equation method or half reaction method. You use that to balance your equation. So you must know it. If you want to know the details of it, go to our previous video. Okay, I want to see how I can do this. I want to use that. We want to use this equation to calculate our value, because 2, what has delayed us is because of this. The amount in moles of this now present in 25 cm cube of solution. Very good. You now know that you have got the moles, you have got the number of moles of dichromate. You have got the number of moles of dichromate. So the moles of iron are very simple from the stoichiometric equation. The equation says we have 1 mole of dichromate reacting with 6 moles of iron 2. So we now have a ratio of 1 to 6. So there are 6 moles of iron 2 that have reacted. Therefore, what do we do? Moles of dichromate, very simple. Moles of dichromate. The moles of dichromate here will be what? Will be, moles of iron here. The moles of iron here will be, from our equation, from the redox equation. From the redox equation, moles of 25 iron in 25 cm cube, we will have 6 times 0.00055, and the number of moles we will have will be 0.00328 moles of iron 2. So now from our equation here, you have known that 6 moles of iron 2 reacted with 1 mole of this, and now we have got the moles of this, the moles of dichromate. So the only way is use the mole ratio. Only 1 mole here. For this to react with this one, you need to multiply here by 6, a factor of this 6 here. So your balanced equation is very, very important. Okay, it takes us to the second part of it. The mass of iron 2 carbonate present in the ore. Iron 2 carbonate. iron 2 carbonate. After doing this, you might be confused. Once more, you might be confused. Here, you can say, once more, you can say, if 1 mole, if 1 mole of dichromate, if 1 mole of dichromate ion could give 1 mole of dichromate ion reacted with 1 mole, 6 mole, sorry, 6 mole of iron 2. Then we are now saying that if 1 mole of this reacted with 6 mole, then how many moles of this? Are you understanding what I'm saying? If 1 mole of the dichromate reacted with 6 moles of iron. Now we have the moles of dichromate. Then 0.00055 moles of the dichromate will react with what? We don't know. So it's just a matter of multiplying. That's all. The value of x, you have it by multiplying by 6. If you cannot understand what I explained earlier, you can just do simple proportion. If 1 mole of dichromate reacted with 6 moles of iron 2, then the calculated moles of dichromate will react with how many moles? Make the simple proportion and you get it. Thank you. Okay. Now, the mass of iron 3 carbonate present in the ore. The mass of iron 3 carbonate present in the ore. What do you need to do about the mass of the iron 3 carbonate? Now, the mass. Okay. The mass here of iron, the mass of iron 2, okay, the mass of iron. So now, you have got the number of moles of iron. You have got the number of moles of iron to be 0.00328. Okay, from this, our triangle, the mole triangle here, what is mass? This is mass. This is moles. Moles, mass divided by moles, we have the molar mass. Moles times the molar mass, we will have the moles times the molar mass, we will have the mass. So this is the relation. This by this, you have this. You go up like that. So in that case, we now have the moles. In order to have the mass, you need to do what? Multiply, use this equation here. Moles times the mass. The molar mass. You want to have the mass. And the molar mass of iron 2 and the molar mass of iron 2 carbonate is what? You need to have the molar mass of the iron 2 carbonate. The molar mass of the iron 2 carbonate is given as iron 2 carbonate is given as, that is Fa carbonate. The M arrow is equals to 11.5.8. That is the M arrow, the molar mass. Therefore, the mass of it will be equal to what? The mass will be equal to the moles from our expression here, the moles times the molar mass times M arrow, or you can call it M arrow or molar mass. Molar mass. You can call it M arrow. And the molar mass is 11.5.8. So now the mass will be equal to what? Will be equal to 0.00328 times the molar mass is 11.5.8. And that will be what? Our final answer will be, for this will be 0.3798 gram. That will be the final answer for it. After multiplying 0.00328 by 11.5.8, we will have 0.3798 gram. Now we go further again. we can now say the percentage of iron 2 carbonate in the sample. The percentage from the mass here, we were told a 5.00 gram sample of the ore was treated with hydrochloric acid and filtered. The filtrate was made up to 250. So in this case, the mass there is original mass is 5 gram. The original mass is 5 gram. So the percentage of iron 2 carbonate in the mass in the sample is supposed to be this mass. The percentage here is going to be the mass that we have got, which is 0.3798 gram divided by the initial mass was 5.00. Initial mass was 5.00 gram times 100 times 100%, and what we will have there will be 7.6%. That will be the 7.6%. Okay, a recap before we go to the B part of it. I said this is redox titration. You have been asked to calculate the moles of dichromate. You have been given the volume and you have been given the concentration. The only thing is what? You need to do this, use the expression concentration equals to mole all over volume in dm cube. Then rearrange to find the moles. And when you rearrange to find the moles, you divide the volume by 1,000. You divide the volume by 1,000. If you are confused about it, this volume divided by 1,000 here, if you are confused about it, this volume divided by 1,000, it will give you this. It will give you this one. The volume divided by 1,000 will give you 0.027. This is it here, dm cube. And the dm cube will cancel the dm cube. If you are really confused, the per dm cube will cancel the dm cube. And you will have 0.02 moles times 0.027, which is 0.02 times 0.027, 73, sorry. If you do that, you will have your answer in a very simple way. You will have no problem. So now you have the number of moles. We have got the number of moles of the dichromate. Now to have the number of moles of iron, you need to write your redox equation. And I have just explained to you how to write a redox equation so that you will know the number of moles of iron 2 that are reacting with the dichromate. And we did that, and we came to a conclusion that our redox balance equation is this one. 1 mole of dichromate is reacting with 6 moles of iron 2. So in that case, since we have the moles of the dichromate, then the moles of the iron, by simple proportion, we multiply by 6, and we will have this. Now, the mass of iron 2 carbonate present. Iron 2 carbonate, we need to use what? To have the number of mass after having the moles. Use this expression. This is the mass here. To have the mass is moles times the molar mass. So the moles times the molar mass will give you this. And the molar mass of iron 2 carbonate is 115.8. And you multiply, you will have this. Now the percentage will be our calculated percentage all over the original, our calculated mass, all over the original mass that was given times 100 will give us the percentage. Now, B part of it, what do you understand by relative atomic mass? What do you understand by relative atomic mass? Relative atomic mass. Relative atomic mass, this is the average mass of naturally occurring atoms. This is the average mass of naturally occurring atoms. Relative atomic mass. average mass of naturally occurring atoms. Yeah, average mass of naturally occurring atoms. Naturally occurring atoms. Naturally occurring atoms of an element. Of an element on a scale. On a scale where the carbon 12, where the carbon 12 atom has a mass of exactly 12 units. So it's just an average mass of naturally occurring atoms of an element on a scale where the carbon 12 atom has a mass of exactly 12 units. You just need to know how to define the relative atomic mass. Then what are isotopes? Isotope in this other case, we say these are atoms of the same element, with atoms of the same element with the same proton number, but different nucleon number. Another word for nucleon number is mass number. I said atoms of the same element with the same proton number, but different nucleon number due to different number of neutrons present. Finish. Atoms, again, atoms of the same element with the same proton number, but different nucleon number, that is mass number, due to different number of neutrons present. And an example, if you define that an example, you can say talk of chlorine 35, and chlorine 30, and chlorine 37. So they are saying these are atoms of the same element with the same proton number, that is 17 and 17, but different nucleon number, different mass numbers. Due to what? The difference in them is as a result of different number of neutrons. You do that, you have it. You have your 2 marks. Now let's go to the mass spectrometer. The mass spectrometer is a very, very important it's an important instrument that is used. This instrument is very, very important because it is used in analytical chemistry. It is used in analytical chemistry. Especially, it is used to determine the relative isotopic mass. It is also used to determine the relative abundance of isotopes. It is also used to determine the relative atomic mass. It is also used to determine the relative molecular mass. And above all, it is used to determine structural formula of compounds in organic chemistry. I said it is very, very important in analytical chemistry because it is used to determine the relative isotopic mass. It is used to determine the relative abundances of isotope. It is used to determine the relative atomic mass of an element. It is used to determine the relative molecular mass of a compound. It is used to determine the structural formula of compounds in organic chemistry. So now we have been given a mass spectrometer here. This is a mass spectrometer. This mass spectrometer, even though, as I said, I apologize for the poor quality of the paper I received. But this is, I have a good version of it that you can easily see. You can easily see. I cannot really, but this is the same thing here. This is a mass spectrometer made up of different heated filaments and the vaporized sample, positively charged electrodes, we'll call them plates. We have, this is the ionization chamber. There is, we call it the magnetic field, ion detector, recorder, and computer, where you can find them. Now let's go to our question. Our question says, on the diagram, label the parts A to D. Okay, these are the parts labeled A to D here. These are the parts. A. From our diagram here, A is a vaporized, these are vaporized sample. These are vaporized sample that will enter here. They are the vaporized sample that are in here. Now, after the vaporized sample, B is what? B, that is, we call them the positively charged electrodes. Or the positively charged plate. These are the positively charged electrodes or plates. Now we go to C. This C here is what we call the magnetic field. The C is what we call the magnetic field. Then we'll go to D. The D part you find in here is what we call the ion detector. Ion detector. Ion detector. So if you can label all this, A as I said A vaporized sample, sample, and then you label B as positively charged electrodes, positively charged electrodes. Then you label C as magnetic field. Magnetic field. Then you label D as ion detector. Ion detector. Ion, not ion, ion detector. Ion detector. Just as you have seen in the ion detector. So if you can label all these like that, A as vaporized sample, B as positively charged electrodes, C as magnetic field, and D as ion detector, just as you find it on the here, then you will have your marks there. Then it takes us to the second part of the question. They said, okay, state what happened at A, B, and C. Remember that at A, what is happening at A? These are vaporized sample. So what you need to do is just what you need to write how the mass spectrometer is functioning. At A, we'll call it vaporization. Just say vaporization. You can say A is vaporization. Okay, vaporization. Here, what you need to do is what? State. Mention vaporization. Then explain. Molecules in a sample, because we say they are a vaporized sample. Molecules in a sample are vaporized to form gaseous atoms. Molecules are molecule in a sample. Can just say molecule in a sample. Molecules in a sample are vaporized. Are vaporized to form what? To form gaseous atoms. You know that for ionization energy, you need to what? You need to atomize, and you can only atomize it to a gaseous state. So molecules in a sample are vaporized. They are vaporized to form gaseous atoms. I'm saying that they are converted to the gaseous phase by heating. I say converted to gaseous phase. That is, they are converted to gaseous phase by heating. That is, they are converted to the gaseous phase by They are converted to the gaseous phase by heating. That is just all that you are supposed to state here. The first thing is vaporization. That is the point. They now mention molecules in a sample are vaporized to form gaseous atoms. Or you can say they are converted to the gaseous phase by heating. Finish. You go now to the second part of it. They say, okay, the second part of it is B. Okay, remember when you now convert when you now convert molecules to atoms, the next thing will be what? The next will be ionization. So B will be what? Ionization and acceleration. Ionization and acceleration. Ionization and acceleration. You cannot explain ionization and acceleration. What happens here? That is ionization and acceleration of, you can say ionization and acceleration of positive ions. Ionization and acceleration of positive ions. What you can now say now is gaseous atoms are converted to positive ions. The positive ions are then accelerated towards the negative plate, with lighter ions being accelerated most. Once more, gaseous atoms are converted to positive ions. The positive ions are then accelerated towards the negative plate, with lighter ions being accelerated most. By just studying ionization and acceleration of positive ions, you already have the marks. So as I've just said like that, you have the gaseous atoms are converted to positive ions. Then the positive ions are then accelerated towards the negative plate. With lighter ions accelerated most. Now the C part of it has to do with what? Magnetic field. The C part of it has to do with the magnetic field. And in the C part of it, what is happening there? There is deflection. There is deflection that is occurring at the, here. So now we say deflection of ions. Deflection of ions. Deflection of ions. Here, after putting the point deflection of ions, you can now state ions are deflected by the magnetic field, and ions with higher charge and a small mass are deflected most. Remember, the size and the charge of an ion determines how it is being deflected. Ions that have a very large charge, ions that have a very high charge, but with only a small size are deflected most. But ions that have big size with a small charge, least deflected. So under deflection of ions, you can now mention precisely that ions are deflected by the magnetic field, and the ions with high charge and small size or small mass are deflected most. That's just all. So that was 2020. It takes us to miscellaneous questions here. We have some miscellaneous questions here that we are going to treat. Miscellaneous question will be on some on titration, still on titration. Okay, the miscellaneous question number 1, it says 25 cm cube of a solution of sodium hydroxide is exactly neutralized by 15.10 cm cube of sulfuric acid of concentration 0.2 mole per dm cube. The equation has been given. Calculate the concentration in mole per dm cube of sodium hydroxide. This is a very good question for you. Remember, I said now you want to calculate the concentration of sodium hydroxide. And only the 25 cm cube of sodium hydroxide have been given. So you cannot go anywhere. You must start but with this one that has been given the concentration and the volume. The relationship that has concentration and volume is what we say concentration equals to moles all over volume. So we can now say that concentration, we can now say concentration equals to moles all over volume in dm cube will be used. So in that case, our number of moles will be what? Will be equal to concentration times the volume in dm cube. By doing like that, we have to calculate what we are going to do, but for sulfuric acid. We are going to do for sulfuric acid. Therefore, we can now say from our data, from data given, moles of sulfuric acid will be equal to what? The moles of sulfuric acid will be equal to concentration. And the concentration of sulfuric acid is what? Is 0.2 times the volume. What is the volume? The volume is 15.10 cm cube. We have to convert it to dm cube by dividing it by 1000. And if we divide this by 1000, we are going to have 0.0151. And in that case, we are going to have the number of moles. The number of moles will be what? The number of moles, when we multiply this by 0.0151, our number of moles will be 0.00302 moles of the acid. Is the moles of the acid. Now, step number 2. This is step number 1. This is step number 1. Step 1. Step 1. Step 2. Step 2. Step 2 now we have to calculate the number of. Step 2. Moles of what? Now that we have got the moles of the acid, now we need to have the number of moles of the base of the sodium hydroxide, the alkali. Since equation has been given, moles of alkali will be what? Moles of sodium hydroxide. The moles of sodium hydroxide now will be what? Mole ratio. Use mole ratio. The mole ratio here is what? 1. The mole ratio here is, in the equation, is 2 sodium hydroxide to 1. The mole ratio is 2:1. 2 of the sodium hydroxide to 1 of the acid. Therefore, the number of moles of, so 2 moles of, in other words 2 moles. 2 moles of the OH will be reacted with what? With 1 mole. With 1 mole of the acid. Reacted with 1 mole of the acid. 2 mole of the OH reacted with 1 mole of the acid. Now that we have got the number of moles of the acid, to have the number of moles of this, as I told you, you can use simple proportion, that if it's just to multiply the number of moles by 2, or just to multiply the number of moles by 2, since its acid is 1 and base is 2, you just multiply it by 2. If you don't know how to do this, please, you can use simple proportion. You can say if 2 moles of OH can give 1 mole of the acid, then how many moles of the, X moles of OH will give what? Will give the number, the calculated moles here. And what were the calculated number of moles here? 0.00302 moles of acid. And the only way to have this, if 2 moles of this can give this, then X moles of the OH will give, how many moles of OH will give this? Simple proportion. Our X moles will be what? Will be equals to 2 times 0.00302, which will be equals to what? It will be equals to 0.00604 moles of what? Of sodium hydroxide. Of sodium hydroxide. That is the moles of sodium hydroxide. We have now got the moles of the acid. This is the moles of the acid we had. This is the moles of the acid we had. This is the moles of the sodium hydroxide we have. After having the moles of sodium hydroxide, let's go back to our equation. We said concentration will now be equal to what? The number of moles divided by the volume in dm cube. We now know the volume of sodium hydroxide, and now we now know the volume, the moles of sodium hydroxide. We can now have our concentration. So now let's take the number, that expression. Therefore, moles of sodium hydroxide can now be, a concentration. Step 3. Concentration of sodium hydroxide. The concentration of sodium hydroxide will be equal to what? Concentration of sodium OH will be equal to what? It will be equal to, we now say, so a concentration of sodium hydroxide will be equal to what? Will be equal to the moles divided by the volume in dm cube. And if we do that, the moles of sodium hydroxide that we just got here is what? Is 0.00604 divided by, that is the number of moles, these are moles, divided by the volume. The volume of sodium hydroxide that was given, was what? Was 25. 25 converted to dm cube would be 0.025. It will be 0.025 dm cube. That's dm cube. Now our number of moles of sodium hydroxide, will be what? Our number of moles of sodium hydroxide will be 0.242 moles per dm cube. Sodium hydroxide. That is the answer. That is how you can do it. Look at the figures, see which information is being given, and look at the relation that you can take. Sorry, please. Excuse me for that. So now, what you need to do here is, you need to look at the information you have been given, use the relation that you want to use. So before you use a relation, make sure you have all the data present. I cannot use the relation which is moles equals to mass all over molar mass, because it is not here. I will now go back to the relation which is concentration equals to moles all over volume, because one of it has the concentration and it has the volume. So I can now it has a concentration and a volume. I can now look for the moles of one, and that was the acid. So that was why we started with this by calculating it. So it takes us to the second question. The second question here is 25 cm cube. 25 cm cube of 25 cm cube of a 0.05 mole per dm³ solution of a metal hydroxide was titrated against a solution of 0.200 mole per dm³ hydrochloric acid. It required 12.5 cm cube of hydrochloric acid to exactly neutralize the metal hydroxide. Deduce, that is based on the information, based on your calculation, deduce, bring out the stoichiometry of this reaction. Stoichiometry has to do with the quantities involved in a chemical reaction. It has to do with what amount of this is reacting with what amount. How many moles of this are reacting with this. So in this case, you have been given information like this one, and what you need to do here, when it comes to calculating this is we have been given the volume and the concentration in one case. In this other case, we have also been given the volume and the concentration. So what is required here is we will use the same relation, which is concentration, which is equal to moles all over volume. And we rearrange it, we will be looking for the number of moles. So now the first thing you need to do here is look at the data before choosing the relation to use. So concentration, the same thing, concentration is equal to moles all over volume. Mole all over volume in dm³. In dm³. So this is what we are going to use here. This is what we are going to use. And in this case, if we arrange this very well, our number of moles will be what? Our number of moles will be concentration times concentration times what? Times the volume. Times the volume in dm³. So now, step number one, calculate. Step one, we need to calculate the moles of the metal hydroxide. We need to calculate the moles of the metal hydroxide. We don't know the type of metal hydroxide. The moles of metal, step one, moles of metal hydroxide. The moles of metal hydroxide. From this relation, the moles will be what? The moles of the metal hydroxide will be what? We have 0.005, which is the concentration, and dividing it, converting this into dm³ will be 0.025. So now we will have the concentration will be 0.05 mole per dm³ times 0. That's the volume, 0.25 dm³. And let's cancel the units out. Per dm³ will cancel this one. Our number of moles will be, our moles will now be 0.00125 moles. That will be the moles of metal hydroxide. Step 2. Let's calculate the moles of the acid. Moles of the acid. Moles of the acid. Hydrochloric acid. God has said it was okay. It required 12.5 cm³ of hydrochloric acid to be neutralized here. So the moles of hydrochloric acid, moles of hydrochloric acid, moles of hydrochloric acid. We are using the same thing here. The moles will be what? Will be, that will be equals to what? It will be equals to the concentration times the volume. And then for hydrochloric acid, the volume is what? The concentration is 0.2 mole per dm cube times what is the volume when we convert 25 cm cube. I mean, when we convert 12.50 cm cube into dm cube, we will have 0. We will have 0.012 5 dm cube. And now we want to cancel out the units. We have this out, is canceling this out. And what will be our value? Our value will be 0.2 times 0.0125. We will have 0.0025 moles of hydrochloric acid. Now that is the moles of hydrochloric acid. That's the moles of hydrochloric acid. Now the next step is step number 3. Step 3 will be the mole ratio. Let's look at the mole ratio. Step 3. Mole ratio. The mole ratio. The mole ratio here, acid and acid or metal hydroxide, that is the alkali and acid. The alkali and the acid. The alkali was 0.00125. The acid was what? Acid was 0.0025. Divide by the smallest. I mean by the smaller one. The smaller one between the two here is this one. Divide by smaller one to have, that is 0.00125. Divide is 0.00125. And now we will have 1 is to 2. So the acid is 2, and the acid is 2, and the alkali is 1. Acid is 2, and the alkali is 1. Then the question says, deduce the stoichiometry of this reaction. That is the quantities reacting. How many of the acid, what quantity of the acid is reacting, what quantity of the alkali. We have deduced it to be 1 mole to 2 mole of the acid. So now we can write our equation. There are 2 equations. Step number 4. Step 4. Stoichiometric equation. Our stoichiometric equation. Our stoichiometric equation will be this one. Let's write 2 equations. Okay, we don't know which one is which. Okay, if the alkali is a group 1, let's say sodium hydroxide. This is going, let's say sodium hydroxide. This is going to be the formula. It will be M metal hydroxide, MOH, plus acid to give MCl plus water. Let's balance it. Let's balance it. On balancing it, you will see that we'll have a 2 here. We'll have a 2 here. we'll have a 2 here, and we'll have a 2 here. Oh, it is not working. It is not working because the question says it is not working because the question says 25 cm cube of the solution of a metal hydroxide was titrated against a solution of 0.2 hydrochloric acid. It required 12 cm cube of this to react, to exactly neutralize the metal hydroxide, deduce the stoichiometry of this reaction. Okay, it doesn't work because why I say it doesn't work? Alkali is 1, but alkali here is 2. Acid here is 2, but acid here is 2. So the ratio does not work. The stoichiometry is wrong. Let's take the other one. So we can now say this one is wrong. This one is wrong. It's not a group. It's not a group 1 metal. So this one is wrong. Now let's take another one again for group 2. If the hydroxide is a group 2, this will be the reaction. It will be MOH. If it is a group 2 alkali plus HCl to give MCl2 plus water. Let's balance it to see. Let's balance it to see. We have 2 chloride here, so we have to put a 2 here. A 2, there will be a 2 here. Okay, the OH here, yeah. There will be 2, but there is a 2 here. There's 2 here. Oxygen is 2. Okay. Yes, but water is 2. Hydrogen here is 2, but there are 4 hydrogen here. There's 2 hydrogen here and 2 hydrogen here. So we need to put a 2 here. We need to put a 2 there. MCl2 is okay. 2HCl is okay. M here is 1, N here is 1. This equation is right. Let's look at the ratio. The acid is what? The alkali is 1. Alkali here is 1. The acid is what? Acid is the ratio 2. So this our equation is right. This is the right equation. So this is our stoichiometric equation. We now call this our stoichiometric equation for the reaction. This is our stoichiometric equation. So that is how you can answer such a question. That's how you can answer such a question. So now, a recap of what we have done. I've done a recap. Yeah, you were given a certain volume, mass of a sample of the iron 2 ore that was being dissolved in the acid, and the thing was filtered off, and finally the solution was made up to 250 cm cube in a volumetric flask with distilled water. From that, 25 cm cube of the standard solution required 27 cm cube of 0.02 mole of dichromate solution for complete reaction. I told you it's a redox reaction. The first thing you see a redox reaction, first try to write the redox equation for it, the oxidation and the reduction. Then you balance it, and then you make the redox equation. You will use that in calculating one section of it. So we did that. We did the calculation. Then we did the calculation for dichromate. We did that using the concentration. We had the moles for dichromate. We used the moles for dichromate to calculate the moles for iron. Since there are 6 moles of iron that reacted using our redox equation, we multiplied it by 6. Then after that, we calculated the mass of iron by using what? This relation. We said mass from this equation here, mass is equal to what? This is mass. So moles times the mass, or up here, you can look at here. The moles here times the formula mass. The formula mass is the molar mass. We will give you the mass. So most times the molar mass will give us the mass. That's the relation we use in calculating the mass of iron 2 carbonate present. Then secondly, we use that percentage of iron that was present and the initial mass that was given as a 5.00 gram to calculate the percentage of iron carbonate in the sample. After using it, we went to the second section of it and we're told, what do you understand by relative atomic mass? And our relative atomic mass, the definition is the average mass of naturally occurring atoms of an element on a scale where the carbon-12 atom has a mass of exactly 12 units. We went to isotopes. What are isotopes? Isotopes, we said isotopes, these are atoms. We said isotopes are atoms of the same element, having the same nuclear number, having the same mass, the same atomic number, the atomic number, but different mass numbers. As a result of what? As a result of different number of neutrons. Then we went to the mass spectrometer, the use of mass spectrometer in determining the relative atomic mass, the relative abundances of the isotopes, the structural formula of compounds, the molar mass of compounds. So we use, I said that those are the uses of the mass spectrometer. It is good for analytical chemistry. Now, using it, I showed you this, that even though I apologize for the poor quality of the question paper, I gave you a copy here of the mass spectrometer, and now I told her A is vaporized sample, B is positively charged electrodes or plates, C is magnetic field, and D is ion dictator. And we're told to what is happening at A, what is happening B, C, and D. There's vaporization there to gaseous atoms. Then there's ionization and acceleration, converting the gaseous atoms to positively charged ions and accelerating it. And an acceleration is based on the mass and the charge of the positively charged ions. Now, I went to D part and the C part, which is deflection of the ions. And the deflection will depend on the mass. Those that have a higher mass or a higher mass with a smaller charge, less deflected. But those with a large, higher charge with a small mass, highly deflected. Then we went to miscellaneous questions or related questions. We have solved this. I told you, you need to take the data before using any relation. And that was what we use in calculating the moles of acid, calculating the moles of the hydroxide, sodium hydroxide, and finally calculating the concentration of the sodium hydroxide. We went to the second one again, stoichiometry, a metal hydroxide and an acid. So only their volumes and their concentration were given. So the only thing was to look for the 2 moles. Look at the moles and see their stoichiometry, the quantity of the alkali or the hydroxide reacting with the quantity or the amount of acid. We did that by calculating the different moles, and finally, after calculating the different moles, their mole ratio, I did the mole ratio by dividing it by the smaller one, and we had a mole ratio of 1 mole of alkali reacting with 2 mole of acid. Then, now write the equation. The stoichiometry there is, you need to write the equation of this. And you cannot write the equation without knowing the ratio of it. So now, I did the first one to show that, okay, take for a metal hydroxide of group 1. Group 1 metal, it doesn't give in the ratio 2:2, so it is wrong. Group 2 metal, it doesn't, group 2 metal, it gave it, so it is right. There's no need going to group 3 metals. So our right stoichiometric equation for this calculation is the second one, which is MOH2 plus 2 moles of hydrochloric acid to give metal chloride and Water. Thank you, fellow listeners for everything you have done, the patience you have taken. I'm wishing you best of luck in your exam. I'm wishing you best of luck in your exam. So if you haven't subscribed to this channel, please try to subscribe so that you can try to subscribe so that you will be getting all our videos. But for those who have subscribed, please, I want to say thank you very much once more for a job well done and for supporting us. Like the video, share it, and make comments. Thank you very much. Have a nice day.